All right, Harrison, we're live. You ready? All right, Mr. Arnold here with Harrison. We're looking at Unit 6, the universe stuff. Really, there are three main things that you need to be familiar with when it comes to the universe stuff. The first one is the Big Bang Theory, which is how we believe the universe started, correct? And also a TV show. The second one is stellar evolution, which is how do all stars evolve, how do they live their life, and eventually what happens to them when they're done living their life. They die just like everybody else here. We have HR diagram, which also is involved with stellar evolution, tells us a little bit about their brightness and their temperature, and finally it's all about galaxies. So those are really the four things you need to focus on for the Unit 6 summative assessment. All right. So according to the Big Bang Theory, we know what is happening, Harrison. The universe is always expanding, and we know it's always expanding because there's really two big pieces of evidence that tells us it's always expanding. Do you know what one of those two pieces are? We can't find the edge, and in fact, as we look as far out as we can, do you know what we find out there? We find stars, but we also find galaxies, and we also find this stuff called background radiation. And, oops, that's a no. Background radiation. And essentially what background radiation is, and they use the term cosmic because it sounds really cool. Cosmic, sorry. And they use it a lot in the comic books as well. So background radiation is the energy that was initially created when the bang went off. So everybody used to say, well, if there was a big bang and it was, started the whole universe, there should be energy out there. Where is that energy? And in fact, they actually found the energy, and they found the energy all the way on the outer edges of our universe. So that's the original start of there. The second thing is, and Harrison alluded to it, is we are expanding. And how do we know that we are expanding? Well, there is no edge, but we actually have physical data because when we look at galaxies, all galaxies are moving away from us. So if everything is moving away, that must mean that everything is getting bigger and bigger and bigger and bigger. And we know that that is moving away because all galaxies are showing us what we call a red shift. Okay? And what a red shift is the wavelengths of the light that's coming off the stars. As we look at the stars today, they are tending to be a little bit more red than they were yesterday. And they're a little bit more red than they were the day before. Red light has the longest wavelength. And therefore, as you move towards the red light area, the wavelengths are getting longer and longer and longer, meaning that the things are getting farther and farther and farther apart. If we had what is called a blue shift, it is in the opposite direction. Things are not getting farther and farther away. Things are actually getting, that's right, Harrison, they're getting closer and closer. So a blue shift is showing us that things are moving towards the blue light. If you notice what I just did to you, I switched the colors. Hopefully you can remember that. So the blue light has the shortest wavelengths. And I'm going to abbreviate wavelengths as WL there. So blue light has really short wavelengths, which means if the light is getting more and more blue, they're getting closer and closer to us.
And what does that mean that faster?
Not necessarily faster, that they're just getting closer and closer to us. Almost everything in the world shows us this red light, red shift. There is one, and it's actually our nearest galaxy, which is called Andromeda, that is showing us a blue shift or a blue light kind of spectrum. That means eventually Andromeda and the Milky Way are going to collide together. Good news is that's not going to happen for billions and billions of years, and you and I won't be here to see it.
So what does that mean? It's shrinking?
It's shrinking its distance, which means it's actually going to...
The galaxy itself shrinking.
No, the galaxy's staying the same size, and it's combining.
If we got the galaxy like a little thing, it would create so much energy.
So eventually, Andromeda and the Milky Way galaxy will be one large, super large galaxy together.
Milky and Andromeda.
Yeah.
I call that.
So, a couple of things to go back over. Big Bang, two real key pieces of evidence that support it. Number one, people were asking where is the energy from the Big Bang, and they found it in the cosmic background radiation. Number two is if this thing is getting bigger, there should be signs of everything kind of expanding, and we know everything is expanding because most things are showing us a red shift, which means the wavelength coming from the light is getting longer and longer. I apologize, Ms. Velardo is done with yoga. There we go. Now we can get back to it. So redshift means the wavelengths are getting longer and longer and longer, and things are getting farther and farther apart. So that's the big thing about the Big Bang Theory. Stellar evolution, I'm going to kind of just walk you guys through this one. All right? So everything starts out as, and everything goes through these first sequences. Everything's going to start out as a nebula. Everything's going to turn into a protostar. And everything is going to go through the main sequence star phase. After that, then the mass of the star is going to determine how it finishes out its life. All right? So we need to know what a nebula is. It's nothing more than a big cloud of gas and dust. All right? That cloud of gas and dust will start to contract because gravity always is into play, even if we're in space. It's kind of like a sneeze. It kind of goes and starts to contract. As it starts to contract, it's going to shift towards the protostar. If you know what a prototype is, Harrison?
The first version of something.
It's kind of the first version of something. It's not the real thing. It's a model. It's a makeup of what it is. So a protostar isn't really a star yet. The gravity contracts. It heats up. It starts to glow, but it hasn't done what it needs to do to become a star. And what that is called nuclear fusion. Nuclear fusion starts about 10 million degrees Kelvin, and that's where it takes hydrogen. It combines other hydrogens together. In fact, it combines 4 hydrogens together to form helium and some energy. Now, this is important because, that should be energy. That energy is given off in light, which is what travels. It hits us. It warms our planet up. It allows us to see. It gives us all the things we need. Plants to do photosynthesis so we can eat. All that stuff happens in this nuclear fusion process.
Actually, a theory about if we didn't have sunlight, we would be like, we'd literally be like vampires. Like, if not like the blood pressure stuff, but
We would have
our
to.
skin would burn.
We would have to adapt to that. Yep. So nuclear fusion starts. Once nuclear fusion starts, you are now a main sequence star. You will continue that process, burn hydrogen, burn hydrogen, burn hydrogen, until you're out of hydrogen. Once you're out of hydrogen, then you start burning some helium. You turn that into carbon, carbon into iron, into other things. But this is where we start our different paths. Our paths are, again, determined by our mass. So if we are a low mass to medium star, which is what the sun is, we're going to follow this path right here. We're going to go from a main sequence star. We're going to slowly run out of hydrogen. We're going to start burning helium. That takes a lot more energy for that to happen. The outer layers of this star starts to expand into space. Space is really cold, so as it expands, it cools off. And as it cools off, it turns to red, so that's where it becomes a red giant. From there, the leftover core is considered a planetary nebula. It'll continue to contract because gravity is going to win out. It'll turn into a white dwarf, which is simply a really hot small star, and eventually it'll turn into a black dwarf and kind of fizzle out. If the if the star is big enough, if it has high mass, it's going to go through step 1, 2, 3 again. But from main sequence, it's going to go down this path. It's going to turn into a red supergiant, just like the sun is going to turn into a red giant. Outer levels are going to expand, etc. from there. From there, when it collapses, though, it's going to go through a supernova explosion. This is what most of you guys have probably heard about or seen in any of the books and stuff from there. From that supernova explosion, it'll turn into a neutron star, which is one of the most densest objects that we have in the universe. From there, if we are super, super high mass, We're going to go through all those stages again. We're going to go through the red supergiant stage. We're going to go through the supernova explosion. But this time we can actually turn into a black hole that's quote-unquote sucking everything in. This is about 1 to 2% of any star or all of our stars that can do that. So very small percentage that actually can do that.
Especially the white hole that actually like pushes out.
So Harrison's question is, what about a white hole? And it depends on what philosophies or theories you subscribe to. There are some people that say the white hole is the opposite end of the black hole, which means whatever is being pulled into the black hole is going to be transported to another area and be pushed back out. And that's kind of that whole time travel-ish kind of things that some people subscribe to believe into. But for stellar evolution, what we need to know is all of these steps are common for all stars up until we get over here beyond the main sequence. The mass is going to determine whether I can go to red giant or red supergiant, and that means whether I turn into supernova explosions or planetary nebula and on down the path. And you will need to know that for the assessment. Those questions are on the assessment. Good on stellar evolution, Harrison? All right, so we got a couple more things to kind of bust through, but these are easy. HR diagram, it's the Hertzsprung-Russell diagram. It tells us two things: the magnitude of the star and then the temperature of the star. So relatively speaking, how bright is it, and then how hot it is. And what you will notice when you look at the HR diagram is there is a cluster of stars that kind of run down this, which happen to be our main sequence stars. Oops. Main sequence stars right there. Our sun fits, I'm going to do it in orange here. Our sun is roughly right about here. It's not too hot, it's not too cold, and it's not too bright, it's not too dim. It's a very average star. Then we have a section kind of up here, which are our red giants, giants, and supergiants. They all kind of cluster right here. And then we have a little section right about here, which are our dwarf stars. They start out as white dwarfs, but eventually they will phase out into black dwarfs and just kind of exist without glowing. So what do you need to know about this? You need to know the position of where they're actually located. So where are the main sequence stars? Diagonally from top left to bottom right. Where are the red giants? Kind of up in the upper right. And then the white dwarfs are kind of below there. You also need to know, what about main sequence stars? Typically, Harrison speaking, as the temperature increases for main sequence stars, what happens to their magnitude or brightness? It goes up, correct. So for main sequence stars, if temp increases, your magnitude or brightness also increases as well. And that's just a function of the hotter it is, the more energy it has, the more energy it has, the more light it can produce. All right, so that's HR diagram. Just make sure you know how to read it, understand what's going on, and kind of how it looks, all right? So last thing here real quick, and I'm not going to spend a whole lot of time as this video is getting a little long, are the three different types. You need to know their shapes. So spiral, Harrison, what does a spiral galaxy kind of look like? Nah, not a football. A spiral galaxy, remember, is going to have arms that kind of come out, kind of makes a pinwheel look to it. And actually our galaxy, the Milky Way, actually has a third arm. It actually has three arms. Kind of like a turbine, yes. Irregular kind of just is what it is. There's no real kind of shape to it. And then your elliptical is a little bit more of your football-ish kind of shape. And the size and the shape kind of tells you what's going on. Irregular tend to have young stars. It's just forming, it's just gaining its shape. As it forms, it starts to develop into a spiral where you have these distinct arms. So these are kind of the young to old-ish. And then eventually the spiral runs out of energy and it kind of just morphs back into it, and the elliptical galaxies there tend to be our more older galaxies that we have. So if you want... Hold on one second. All right, we're back here. So if you take a look, if you wanted to know where our sun is roughly about halfway out on one of the arms. We are about 20 to 30,000 light years away from the middle, and we're about 20,000 light years to the end of our arm in our galaxy. So we're kind of sitting in between those kinds of things. So what do you need to know? You need to know a little bit about the shape of the galaxies. You need to know a little bit about their relative ages, and a little bit about where we are here in our own galaxy. Questions? We're going to leave it at that. As always, if you have any questions, please come see me. Harrison, you got anything for all the people out there listening?
Have a great day.
Harrison says, have a great day.